Hello and welcome to another lecture of classical motion of a single particle. In this lecture, we simply continue our discussion on the motion of a particle with respect to a non-inertial frame of reference. So, just to recapitulate a little bit, so non-inertial frames of reference are those in which the Newton's laws are not valid. Okay. So, for example, if you calculate the m times d2r dt2 with respect to that reference frame for any arbitrary particle, and if from your knowledge you know that F external is the amount of net external force which is acting on the particle, then F external will not be equal to m d2r dt2. Okay. So, of course, we already have seen the solution for that. We have said that in order to make Newton's laws valid in such reference frames, we need to add some forces which are known as pseudo forces. Okay. Although the pseudo force has no existence with respect to an inertial frame of reference, the pseudo force can be experienced by an observer who is sitting on a non-inertial frame of reference. Okay. And so, for that observer, pseudo force may look real. Okay. So, for example, whenever you are traveling in a train and the train slams brake, okay, then you actually get a little bit perturbed. That is actually because of the pseudo force. Okay. And of course, again you have seen that if you have like a rotational type of motion, then of course you can be supposed to be an observer in a non-inertial frame of reference, because any rotational particle is actually accelerating, that we all know. And of course, that if you now want to study the motion of any other particle, then you have to take all these pseudo forces into account, so that you can match your results of dynamics with your friend who is, for example, sitting in an inertial frame of reference. Okay. So, here I can give you the formula for relating the ddt of an inertial frame of reference and a rotating frame of reference with respect to that inertial frame of reference and sharing the same origin. Okay. So, we said that if dA dt is the time derivative of any arbitrary vector A in the inertial frame of reference, and dA dt would be the time derivative of the same vector in the rotational frame of reference sharing the same origin, then there will be just an extra term in this side which will be omega cross A, where omega is the angular velocity of rotation of this rotational frame of reference. Okay. And immediate conclusion from this, we have seen that if you have a vector A which is parallel to omega, then for that dA dt, okay, if omega is this, then dA dt inertial will be exactly equal to dA dt rotational. Okay. So, otherwise of course, this is not true, but in general we can write the Newton's laws for a non-inertial rotating frame of reference moving with an angular velocity omega, which need not be constant, okay, is given by m d2r dt2 rotational will be equal to m d2r dt2 inertial minus m omega dot cross r minus 2 m omega cross v, okay, minus m omega cross r. Okay. Now, of course, we have said that this is known as the Euler force, this is known as the Coriolis force, and this is known as the centrifugal force, and all these three forces are non-existent with respect to an inertial frame of reference, and they are known as pseudo forces. Okay. Pseudo forces. Okay. this one is exactly equal to the net external force, because in inertial frame of reference Newton's law holds good. Okay. So, if we now know this one and we know this all information, then actually one in principle should calculate m d2r dt2 with respect to a rotating frame of reference. And we have specifically mentioned that this information or this calculation is necessary for us, especially who are living on earth, because you see that earth is moving with respect to sun in an orbital motion. Okay. Earth is also spinning. In both cases earth is a non-inertial frame of reference. Now, I, for example, who is sitting on one point on the surface, at one point on the surface of earth, is also rotating with respect to earth and actually executing two motions. I am actually spinning with respect to the spin axis of earth, and along with the earth I am also rotating around the sun. Okay. So, in both cases I am a non-inertial frame of reference, and that is why I need all these pseudo forces to include in order to make Newton's law valid in my system. Okay. So, with this I can now just try to tell you some interesting fact about those pseudo forces. So, as I said yesterday that this is known as Euler force, and this is exactly of not that much importance for earth, because for earth what happens that omega is almost constant. Okay. So, if we of course consider the spin motion of earth or the seasonal motion of earth, okay, in both cases you will see that the omega is actually pretty constant, because you know that the earth takes almost 365 days every time to make a complete rotation with respect to the sun or around the sun, and also it takes 24 hours to make a complete rotation with respect to its own spin axis. Okay. Since omega is almost constant, that omega dot is actually not that important, but somehow some effects can be revealed if you also take this term which is known as Euler force. Okay. And this term is known as Coriolis force. Coriolis force. Okay. As I said that this term is actually perpendicular to both omega and v, and that is why this is a no work force, and this force is non-zero only when the particle whose mechanics or dynamics is getting studied has a non-zero motion in the non-inertial frame of reference. Okay. So, for example, if I am simply sitting on the surface of earth, then I will not feel a Coriolis force, okay, due to the spin motion of the earth. Okay. Now, if I consider myself running or walking on the surface of the earth, or I consider some river is flowing on the surface of earth with some velocity with respect to earth, okay, then of course, there will be the question of Coriolis force. Okay. And I said this is Coriolis force is also very important for air. Okay. Let us just try to understand one very interesting problem which is very important for atmospherical physicists or atmospherical scientists and also geoscientists, okay, and meteorologists as well. So, that means the people who are doing weather forecast, is that how the air get deflected, okay, when it flows very close to the surface of the earth due to the Coriolis force. So, I just tell you just using this formula how to understand the deflection. Okay. So, I can do something like I can draw the earth like this, okay, and this is the axis of spin, and the earth is actually moving from west to east with a constant angular velocity omega, and this is the equator. Let us say this is the northern hemisphere, this is the southern hemisphere, and let us say air is moving very close to the surface, okay, air is moving towards the north pole, okay, right from the equator. So, this is north pole and this is south pole. Okay. Yeah. So, Now, the point is that will the air be deflected. Okay. So, as you can easily understand that this air is actually moving. So, if you now see from this side, then you will actually can see okay, the air is actually moving like this, okay, and your spin axis is this. Okay. So, very close to the equator there is actually no force of deflection, because omega and v they are almost parallel. Now, when it becomes here for example, okay, then what happens that this v gets an angle with omega, and you will actually can see that this omega direction is if like this, then in northern hemisphere the v direction is like this. Okay. Now, you just have to calculate omega cross v, and even if you do not calculate the whole thing, you just have to understand the direction. So, omega cross v, okay, with a minus sign is nothing but v cross omega. Okay. So, I can actually say okay, this will be, so you see in this type of diagram where I can have something like this, if this is the earth surface. Okay. So, I can actually say that, and omega is I can parallelly I can shift it here. Okay. So, v cross omega with the right hand corkscrew rule, it should go to the direction inward, okay, of the with respect to the plane of the paper. Okay. And so, with respect to this picture, that means that the deflection will be in that direction. Okay. And you can say that okay, my air is actually getting deflected in this direction. Now, if the air is moving from the direction of the north pole and towards the equator, then what happens? Okay. Then it will actually have a velocity which will be just like this, but now it is downward. Okay. So, you will have again omega cross v with a negative sign, which is v cross omega, then it will be okay, outside of the towards the outward direction of the plane of the paper. So, it would be like this now, and in this diagram it will be like this. Okay. You can do the same thing for the southern hemisphere as well. For southern hemisphere what happens, you can actually understand the whole story like this. So, if you have this, so just you have the direction here as well, this is the direction of omega, okay, and then from the southern hemisphere if some air okay, is going from the equator towards the south pole, okay, then its velocity will directed like this. Okay. And so, the Coriolis force is always minus omega cross v. So, if I also say that minus omega cross v is v cross omega, I know, but it is also true this is exactly equal to minus omega cross v. So, if my v is now in this direction, okay, and minus omega is in this direction. So, again you will see that minus omega cross v will be actually, so minus omega cross v will be to the inward direction of the plane of the paper, and that is why you will have this type of deflection. Okay. And of course, now just by similarity you can think that okay, if I have air which is moving from southern pole to the equator, then it will also move just by symmetry in this direction. So, this can be concisely, this can be condensed into a form of a law, where you can say that okay, if on earth air moves in the northern hemisphere, then it always gets deflected towards the right. Okay. So, for example, here it is deflected towards the right, here it is also deflected towards its right, because when it is moving in this direction, this is its right, and in the southern hemisphere it is deflected towards the left, and this is also true here, and this is known as Farrell's law. Okay. And Farrell's law can actually determine the direction of the air current and the wind, of course, okay, which are moving on the surface of earth. Okay. Now, we can do something much more sophisticated, that is, last time we said that how to relate two frames of reference, one is inertial, another is rotating, but sharing the same origin. Now, let us say I have a new case where I have two frames of reference. The first one is of course x, y, z and still inertial. The second one is now rotating, but it is no longer shares the same origin. So, let us assume that origin to be q, okay. And we are now trying to see how the dynamics of a particle which is situated at P can be studied with respect to this non-inertial frame of reference. So, once again try to understand, this one is another frame of reference which is rotating with respect to some omega cap direction, okay. And we just know that the position vector of the origin of this q is actually with respect to this unprimed coordinates is r, capital R. Okay. Now, this second frame of reference is actually rotating with its origin making some arbitrary motion that we do not know, okay, that may or may not accelerate with respect to this unprimed coordinate. Okay. Then what happens, we can actually say that if we want to now study the motion of P with respect to this second coordinate system or second frame of reference, we actually should draw the position vector of this here, and that should be given by small r vector. And we want to actually find the second order derivative of this small r vector with respect to time. Okay. That will give us the acceleration of P with respect to this non-inertial frame of reference. Okay. I can draw a third side to complete the triangle. Okay. So, I can actually make the triangle a little bit better. So, I can make the point under consideration whose motion is being studied to be P, okay, and from O to P I now make a new position vector which I call a rho. Okay. So, this is actually small r, okay, yeah. And now, we want to calculate m d2 r dt2. Okay. We know from the normal vector algebra that this rho is equal to capital R plus small r, and that is why d2 rho dt2 is simply d2 r dt2 plus d2 small r dt2. Okay. If I do this, then I do not know the exact nature of the motion of this origin of the rotating frame of reference. Sorry, I have to put the z axis somehow. So, I can call them as small x, small y, small z. Okay. Yeah. So, this center can actually move in a uniform velocity. This center also can accelerate. Okay. That will be evident from the motion of this observer with respect to this inertial frame. Okay. Plus you have this thing. Now, this thing you have already calculated. Okay. If I just want to write in a proper way, you know that this thing will now be, so m d2 r small r dt2, that will be equal to m d2 rho dt2 minus capital R double dot, okay. I am just writing in a concise way, times m minus 2 m omega cross v, okay, minus omega dot cross r times m, okay, minus m omega cross r, okay. If I can do that, I am actually all set for studying the motion of a particle p with respect to the rotating frame of reference x small y small z, whose origin or the center is also moving with some motion, okay, and is placed at the point q, okay, and this motion is given by this term. Okay. Of course, if r is now constant, it is not moving with time, it is not changing with time, then finally again we will have the old formula which we derived last time will be recovered. Okay. Now, what to do with this formula? We can actually, with this formula, we can try to study the motion of a particle with respect to earth and with respect to some observer, okay, who is sitting on the surface of the earth. So, that will be a fantastic problem to treat, and that will be actually a very important problem. So, just to try to understand that if someone with her or his telescope is studying the movement of some planetary body or some, let us say, some star in space, okay, some astronomer, okay, then how to actually make the Newton's laws of motion valid with respect to her or his conclusion. So, we have to actually use then this type of equation, and of course, these equations will now be simplified, okay, when we are specifically considering that this non-inertial observer is someone who is standing or sitting on the surface of the earth, and that we will now do. Okay. So, you see that if I am now just talking of earth, so the first simplification comes that I can get rid of this term, because omega is constant to a good approximation. That is why omega dot is 0. So, I can say this is 0, okay, a null vector. Okay. Then I can also say that this one is equal to, so I can also say that m r double dot, okay, that will be equal to the acceleration of a particle of an observer who is sitting on the earth surface. Okay. So, that we can use. Okay. What will be the expression, that we will see in a minute. Okay. And this one, this is the d2 rho dt2 times m. So, this is the accelerations times the mass of the particle which is situated at p with respect to capital X, capital Y, capital Z in a frame of reference, which is an inertial frame of reference. So, this one will be exactly equal to the force external acting on the particle, and that we can use from our knowledge. Okay. Now, how to really calculate the motion or the study of motion, okay, with respect to an observer who is sitting on the surface of the earth. So, for that we have to actually draw the situation a little bit more clearly. So, this is the surface of earth, this is the center of earth, okay, and someone is sitting here. Okay. So, let us say capital R is the radius of earth, and this person is somehow doing some sky watching and studies the motion of some celestial bodies. Okay. Now, what about the person's R double dot? Is this fixed? Of course, the modulus R is fixed, but you have to understand that the person is actually moving with respect to the spin axis of the earth, and it actually moves with an angular velocity omega, which is corresponding to the spin motion of earth. Okay. So, here before I start anything, I have to just say that since the angular velocity of the spin of earth is quite important with respect to the orbital motion of earth with respect to the sun. So, for the current study we first do a simplification, that is we neglect. So, okay, just to write, in order to study the motion of a particle with respect to an observer standing on earth, okay, standing on earth, we neglect the effect of seasonal motion of earth around the sun, okay, that we neglect. So, if it is, for example, if it is sun and earth is moving with respect to sun in an ellipse, you now know, then at any position the earth is actually acting like an inertial frame of reference, this position. Okay. So, I can actually think that if I just take that position, because with respect to the spin motion of earth, okay, this motion is quite slow, and that is why you can think that I can have many spin motions, okay, when on this ellipse the earth is actually advancing by a very small amount. So, I can actually think that just for one spin motion the earth is actually at rest on that ellipse, but it is simply spinning. Okay. So, if I now consider a set of coordinate axes and an observer, a frame of reference, okay, which is not moving or not spinning with earth, but it is simply fixed with its center to be coinciding with the center of the earth at one point on that big ellipse, okay, then that reference frame I can consider to be inertial. Okay. Now, I will take another reference frame. So, you see the two frames of reference will now be defined like this. So, you have two frames of reference. One is this one where this x, y, z, which is not moving or not spinning with the other part of the earth, okay, and there is me or a person, man, okay, who is sitting or standing on the surface of the earth. Okay. The person should look like this. Okay. And for that person, you will see that that person is actually spinning with respect to this inertial frame of reference, but the person is having now a coordinate axis attached to this, which is here. Okay. Some small x, small y, small z. We want to now study the motion of a particle p with respect to this coordinate axis, okay, and the person's situation or the position is given by this capital R vector, and the double dot will simply be due to the person's spin motion with respect to the earth spin axis. Okay. So, now with respect to this inertial frame of reference, okay, whose origin is situated at the center of the earth, the person's frame of reference is having a center which is displaced by r distance, capital R distance, this distance, okay, and is actually moving in a circle like this. Okay. So, I can actually draw a better picture so that you can all understand. So, this one can be helpful. So, this is the center of the earth where you are assuming that you have an inertial frame of reference, okay, that is x, y, z, and then you have a person who is sitting over here, and this person is actually having some inertial, some other frame of reference which is not inertial of course, and the origin is actually spinning. Okay. So, because I have here just considering that this is the spin axis. So, the spin direction is coinciding with the direction of omega for earth. So, I can actually say that omega is exactly equal to omega times capital K cap. Okay. Then I can say this one is simply moving with this. This point is just rotating, okay, like this. Okay. So, you see that then this person is actually spinning, okay, and since this person is actually spinning with respect to earth, then for that person with respect to an inertial frame of reference, r double dot will be simply given by the centripetal acceleration. This, okay, because this is just the, this is, you understand, this is just the motion of this person with respect to this capital X, capital Y, capital Z frame of reference, okay, and this is a motion where it is actually having a position vector r and it is moving with a angular velocity omega. I can, sorry, we can angular velocity capital omega, sorry, and then you have this. So, the acceleration is given by simply the centripetal acceleration. This is not a pseudo force here, this is a real force. Okay. Now, what will be this quantity, this m d2 rho dt2, okay, what is the F external? So, F external will simply be the gravitational force, okay, due to the gravitational interaction of this mass particle here P, which is having a mass small m, and earth. So, now the earth can be considered to be point mass and the mass is concentrated at its center m. Okay. So, if you just take this point to point gravitational interaction law of Newton, then you know that this will simply be given by this F external will be exactly equal to minus g capital M by times small m by rho cube times rho unit vector. Okay. That much you can know. With all this thing, now I am all set to write the equation of motion for the particle with respect to this observer, which I can call q. Okay. So, this is actually r vector, okay, and once again this is badly drawn. I have to actually have to draw here, right. So, this is small r and this is actually your rho. Okay. So, I can now write m d2 r dt2 will be equal to minus g capital M small m by rho cube rho cap minus m. Now, instead of r double dot, capital R double dot, I wrote omega cross r, okay, and I can also write minus 2m omega cross v, okay, minus omega. So, this v is again the velocity of the particle with respect to this non-inertial frame of reference. So, if you try a clarification, that will be this dr dt, okay, and finally it will be m omega cross r, okay, that will be all. okay, we are neglecting the Euler force. Now, if we have all this thing, we can actually realize that this thing is along this rho cap direction, and this thing is actually this omega cross r. This is all actually something which is radially inward. So, if you just simply think that I can just say that my effective gravitational acceleration of the particle with respect of this particle p with respect to the observer sitting on the surface of earth is given by g minus, so I can write g should be minus gm by rho cube rho cap minus omega cross r, because this is a constant term. Okay. So, and this is actually you see, so that is an attraction force, okay, due to the mass interaction. So, it is a gravitational interaction between the earth and the particle, and this is a part which is actually now, so this one is with this minus sign is acting radially inward, and this one actually with this minus sign is acting outward side. Okay. So, you can actually think that okay, so this part can actually somehow counterbalance even partly this part, and that is why this g will be your g effective. Okay. If you write this, then finally you can write this thing much easily, then it will be m g minus 2 m omega cross v minus m omega cross r, okay, small r. Now, already you see that this is the acceleration of a particle with respect to an observer who is sitting on earth. Okay. Now, another approximation is that if the particle is situated very close to the surface of the earth, that means modulus. So, if modulus of r is very less than modulus of capital R, then you can even neglect this term, and finally, you are left with only this equation. Okay. So, although we have started with many terms, you see that some simplifications are going on, and you can actually write okay, so the equation of dynamics of the particle with respect to an observer standing on the surface of earth is given by d2r dt2 is equal to g. So, g is actually g effective minus 2 omega cross v. Okay. So, once again you try to understand that I have this effective g, I have this Coriolis force, and this I just neglect. So, finally, I have these two sources of interaction, and this one is the only. So, if I just write mg and m this. So, this one is the main force which is acting on the particle on the particle. So, you see that it is the Coriolis force. Coriolis force. Okay. And That is why the effect of the Coriolis force is the most prominent one when we are studying the motion of a particle very close to the surface of earth. Okay. Just before wrapping up this lecture, I will do a little bit more. So, I will now just draw this thing, that if I say that okay, this is the center of the earth and this observer Q, who is sitting on or standing on the earth surface, is actually at a co-latitude lambda. Okay. So, that means that the angle between its local vertical, okay, or we can say that small z direction and the capital Z direction, they are making an angle lambda. If you make this, I can say this is the capital K cap direction, this is a small k cap direction. Okay. Then, and I also can choose that. So, if this is co-latitude lambda, then the latitude will be 90 degree minus lambda. Okay. Then one can actually choose, without losing any generality, the x direction will be the small x direction, of course, the I cap direction will be along the tangent plane of the surface of the earth. Okay. And then of course, the final one. So, if x and y should be following, should be giving z direction by right hand corkscrew rule, then y cap should be, now you know this, the meaning of this symbol, that is this should be directed towards the inward direction of the plane of the paper. Okay. If I have this, then I can write this capital K cap is exactly equal to capital K cap dot small I cap, that you always write any arbitrary vector in an arbitrary coordinate system like this. Okay. So, capital K cap dot j cap times j cap. So, these are simply the scalar projections of capital K cap vector in those directions. Okay. Then capital K cap dot small k cap times small k direction, small k cap. Okay. Now, what is this thing? This is nothing but cos lambda, okay, because both capital K, small k, all of them are actually unit vectors. So, just the their dot products will be simply the cosinus of the angles between them. So, here you see that will be simply cos lambda plus cos lambda. So, I can write cos lambda k cap. Okay. Now, if this is in this direction and the y direction is perpendicular, is the inward direction, okay, to the plane of the paper, then z, then k dot j cap will be 0. Okay. And what will be this one? This one will simply be, so you have to have an angle which should be, so with z you should have an angle over here. Okay. So, which should be 180 minus yes. So, if this is lambda, so then this will be 90 minus lambda, and that is why this will be 180 minus 90 minus lambda, which will be 90 plus lambda, and that is why when you write this, it will be cos 90 plus lambda times I cap. Okay. So, it is 0 j cap. So, you see once again, so this is the direction of the I cap. Okay. This is the direction of the I cap. Here I am just making this, and this is 90 minus lambda. So, this is actually 180 minus 90 minus lambda, which is 90 plus lambda, and then if you take the projection in this direction, that will be simply this, and cos 90 plus lambda, we all know this is minus sin lambda I cap, plus then you have cos lambda k cap. All these are small I cap and small k cap. Okay. If I have this, then I can actually calculate now omega cross V, because V is omega is now, you know that sorry, I have made mistakes. So, here this omega should be replaced by capital omega, yeah, and here the same thing I can actually write that my omega cross V will simply be equal to capital omega capital K cap cross, now x dot, I would simply say, sorry, x dot small I cap plus y dot small j cap plus z dot small k cap. Okay. If you do the calculations clearly, you will, so what we have to do now, you know this is this, so it will be minus omega sin lambda I cap plus omega cos lambda j cap cross x dot I cap plus y dot j cap plus z dot k cap. Okay. You do these calculations carefully, okay, and you will see that finally what you will get will be just given by x double dot will be equal to 2 omega. I can actually do these calculations with you. So, this is not a very big deal. So, omega cross V I can write like this. So, I j k, so it will be omega minus omega sin lambda omega cos lambda, it should be k cap, sorry, k cap, yeah. So, minus omega sin lambda 0 omega cos lambda, then I will do x dot y dot z dot, x dot y dot z dot, then I will do, so this is omega cross V, okay. Then I will have I minus omega cos lambda y dot plus, so with I will have this minus this, right, plus j I will have x dot omega cos alpha minus of minus, so plus omega sin lambda, sorry, z dot plus k cap minus omega y dot sin lambda. Okay. So, I have this part with a, so, and also I can now write this. Okay. You will see that here in this direction you have this g. So, this g will be actually, if you remember, by definition it will be actually directed towards the radially inward direction, which is minus z direction. So, if you consider everything, then you can actually have x double dot will be equal to this so there should be a minus sign. So, I can just erase everything, yes. So, the equations come from this, r double dot should be equal to g minus 2 omega cross V with m multiplied, so that it is the equation for the force. Okay. So, I can actually write, to be very precise, this will be now equal to, so you have something like this with a minus sign along I cap, this will be, this is omega cross V. So, this will be actually plus, so 2 m omega cos lambda y dot. Okay. For y cap for y double dot, m times y double dot, I will actually have this whole thing with a minus sign. So, it will be minus 2m omega cos lambda x dot plus omega sin lambda z dot. And finally, for z double dot you will have minus g, okay, which is, so you see here the z small z direction and the r cap direction, okay, capital R cap direction, they are actually the same. Okay. So, you will have minus g and then there will have plus 2 m, of course minus mg here, plus 2 m omega sin lambda y dot. Okay. So, these equations constitute the essential equation of dynamics to study the motion of a particle near to the earth surface with respect to an observer who is sitting or standing on the earth surface. Okay. So, now according to the different type of initial conditions and boundary conditions on displacement and velocities, you can actually solve for x, y and z and thereby solving x dot, y dot and z dot. Okay. One very simple example I can leave it to you as an exercise is that solve for x, y and z if the particle is starting from rest and from a distance h on the earth surface, okay, small h. So, that means that at t is equal to 0, x dot equal to 0 equal to y dot equal to z dot, okay, and x is equal to 0, y is equal to 0, but small z will be equal to h. So, when we say there is a distance or from a distance small h from the earth surface, this distance is actually along the small z direction. Okay. So, you just calculate this and let me know what you get. Okay. Thank you very much.